much with it. There is the idea where you could have like lots of wires, and they could lasso a couple of them and ask, which one of these Amperian loops has the largest amount of magnetic field, or the least amount of magnetic field, or most amount of enclosed charge, or the least amount of enclosed charge. Those, they don't usually ask those kinds of questions. They save that for Gauss's law. But they will ask this one, and this one can be kind of tough for the uninitiated. So let's consider first a long current carrying wire where we have something like this, a cylinder looking thing. And I would encourage you to draw it big enough because we're going to need to make some drawings inside the wire. All right, so the idea is that we have a long current carrying wire. And for this argument's sake, let's say the current is traveling this way in the wire. Now, none of what I'm about to say is actually true. This is not how current works. And these questions, although are in the literature, they're a little bizarre in that this is not really what's happening inside a wire. And we kind of know that. We know the charges are all on the outside edges of the wire. We know that the charges themselves tend to still repel each other, or repel away from each other. But these problems are more mathematical exercises than they are actual physics. But they're still part of the literature, so we have to be familiar with them. The question tends to be, what is the magnetic field inside the wire due to the motion of the charged particles as they pass through the wire? I'll say it again. They ask, what is the magnetic field inside the wire due to the motion of the charged particles passing through the wire? They've done both cylindrical wires like this one, a solid cylindrical wire. They've also done like coaxial cable, where it's got a inner hole through the wire and then an outer thick ring of wire. So they've done both. And these should remind us of like the sphere of charge problems that we had for electrostatics, where we were asked to find out the electric field inside a large sphere of charge, usually not a conductor of charge, but an insulator made of all charged particles, where we had to find the electric field inside, and then how did the electric field behave outside. So they'll usually ask you for an expression for the magnetic field inside the wire, and in addition to that, they'll tend to ask you to maybe sketch or draw a graph of what the magnetic field would look like both inside and outside the wire. So that's what we're looking to derive. Now, there's a couple things about this that we need to probably throw from the very beginning. Some parameters. They're likely to offer us something like the wire has a diameter of r, or a radius of r. I'm going to use a radius, not diameter. Generally, they'll give us that there is a charge traveling through the wire, or a current in the wire. They'll say one or the other. They could tell us how much charge is moving through the wire and its velocity. That's unlikely. They've only done that once in the literature. Often they'll give us a current value, like they'll say I or something like that. And then we are to derive a current density from that. And we've talked about current density before, but we don't talk about it often. This is an easier version of current density than us looking at the motion of charged particles. This is usually nothing more than I divided by A, where A represents the area, the cross-sectional area of the wire. Now, it shouldn't be a huge surprise that if the current is traveling in the direction indicated. There is a magnetic field that's traveling in a circular direction inside the wire. Just using the right-hand rule should tell us that. Kind of putting my thumb in the direction of the current, or in this case, into the board. And we should have these rings of magnetic field inside the wire. And the reason for this should be that in any one of these rings, inside of it is the motion of charged particles due to the current. So outside of it has to be a magnetic field produced by the motion of those charged particles. We know there'll be a magnetic field outside the wire. We know that from looking at Ampere's law. But Ampere's law also tells us there's a magnetic field inside the wire. So we're going to try and find an expression for the magnetic field. And I'd like to draw this a little bit clearer. So let me give myself a little bit better. We'd like to find the magnetic field as a function of little r based on being some distance away from the center of the wire. Now, this isn't a particularly hard derivation, but we don't use Ampere's law very often. So when it comes to using Ampere's law, there are a few things I want to remind you because it doesn't come up. Ampere's law is an integral, but it's one of those integrals that we try not to use. It is mu naught times I enclosed equals an integral of b dot ds. It's a dot product. And it's integrated over a closed loop. So when we're doing an Ampere's law problem, we select a loop, a lasso, that we put around our current. In this case, we're going to create the lasso located at lowercase r. That's where our lasso is going to be. Now, there's a couple things we have to do here. I don't think there's too much, but there's a few things we have to do. First, we're going to have to come up with an expression for the enclosed charge. And this expression is the enclosed charge in terms of lowercase r. And we're going to use the density for this. It shouldn't be a surprise that we're going to take the current density, J, and we're going to multiply by the enclosed area. And this is going to be the enclosed current. You remember doing this for enclosed charge before, right? For electric fields. It's been a long time, I know. We're doing the same kind of calculation here for Ampere's law as we did a long time ago for Gauss's law. Now, again, our current density isn't going to be hard to deal with. It's going to be the I that we're given divided by pi capital R squared. It's our current density. And it's based on the geometry of the wire. As you'd expect, our enclosed area is going to be based on the lowercase r, representing the radius from the center of the wire to where our Amperian loop has been drawn. And this produces a current that's based on a ratio. The pi cancels out, and we get this ratio of little r squared to big R squared. And all of this is our enclosed current. Now, the magnetic field part is kind of ridiculous in its simplicity, and we're trying to design it this way. When I say ridiculous in its simplicity, remember the goal here is to not actually integrate. Our goal is to have a simple length. as the result of integrating ds, and to try and make our magnetic field constant so that it comes outside of our integration. So we do that by exploiting symmetry in our problem, drawing the loop in such a way that it's centered and concentric with the center of our wire. And then turning this directly into a pretty straightforward integration that will give us a circumference. Now, we can only do this if a couple conditions are met. And please, don't neglect these conditions, because our very next example after this, these conditions won't be met. Condition number 1, the magnetic field has to be a constant on the loop. Condition number 2, the magnetic field has to be in the same direction as our loop. We haven't made that test yet. And condition number 3, it has to be a completely closed loop. Now, in this example, we're kind of guessing. We are assuming the magnetic field to be circular around this loop, so that at any point on the loop, the magnetic field vector would be tangent to that loop. We're also kind of expecting that we integrate in the same direction as the magnetic field, which makes perfect sense. I mean, we want to make sure that our cosine works out here. This is a dot product. We are trying to effectively create the condition for the angle between ds and the magnetic field to be 0. That's the second condition there. The magnetic field is in the same direction as the loop. We want the angle to be 0 so that our dot product isn't a thing. That's what we're trying to do. That way we can pull the b right out of the integral, say it's a constant, and be left with adding up this length, which, for all intents and purposes, is just going to be 2 pi times little r. Which has to equal mu naught I total times r squared over the radius of the wire squared. Which, by the way, gives us kind of a weird result. When you solve this for b, you're going to get the mu naught I that we've come to expect and 2 pi capital R squared in the denominator times r. Right, one of the r's will cancel out. Now, this result is important, and I really want you to hear this. This is linear. The magnetic field increases linearly until you get to the edge of the wire. So if you're asked about this, it should be expected that you get this kind of weird result. Now, I say weird because our wire is a conductor. Technically, all the charge should be on the outside edges of the wire. We should have no electric field in the wire. We should find no charges in the wire. So they'll put these graphs out there that show no current inside the wire until you reach the edge of the wire. And the truth is, that's probably what's really happening. But these current density problems suggest a classical view of the flow of charged particles in the wire as they pass through the middle of the wire. But we also believe that all the charges are on the outside edge of the wire. Which of these things is true? And the answer is, I don't know. If you have a test question and they're asking you to figure out the magnetic field inside a wire, this better be what you do. And you better come up with this result. And if it's on the multiple choice, and we assume there is a magnetic field inside the wire. We're going to assume that when current is passing through a wire, that the current is uniformly distributed inside the wire, and that its current density can be calculated by just taking the entire current and dividing by the cross-sectional area of the wire. That is what we're going to assume, even if it's complete BS. Now, I will point out this problem shows up in two versions on the exam. One where the charges aren't moving, and you're first asked to calculate the electric field inside the cylinder, and then one where they click the current on and you're asked to find the magnetic field inside the cylinder. The second version of this problem is one that I don't think we'll see because they haven't asked it in a long time. But you know that the moment I say that will be the year that we do have to do it. And they'll have our wire be a hollow cylinder with current passing, on the outside, but there's a hollow, tube down the center where there's no current at all. Now, they haven't asked that question in a while, but you do know that I'm probably going to give it to you in a couple of days as a practice FRQ so that you've at least seen it. All right. Pretty straightforward, I think. Not a whole lot here, but you understand why I kind of saved it for after our test, to kind of look at this little piece. The next thing we're going to talk about is actually quite practical. And when I say practical, this is one of the things we're going to be making later this week. We're going to be making solenoids. Solenoid is the number one way to make a magnetic field. It is the number one way, which is why we tend to study solenoids. A solenoid is a fancy word for just a bunch of coil of wire. That's all it is. You take wire and you loop it a lot of times. You're making a solenoid. The idea here is currents going in and coming out. But we already know that a single current loop produces a magnetic field that's equal to mu naught I over 2R. Right, we did that calculation a couple weeks ago using Biot-Savart. So a single loop of current produces a magnetic field. This was assumed at the center of the wire to be the size of the magnetic field. Well, it shouldn't be a huge surprise that if we could get lots of loops there, then we can increase the size of that magnetic field. Right? We double the magnetic field by doubling the number of loops. So the more loops we can put together, the stronger the magnetic field. Now, a solenoid actually tries to do two things at once. The first thing it tries to do is what I just said, increase the size of the magnetic field by amplifying the number of loops. But the second thing it tries to do is it tries to collimate the magnetic field by trying to straighten out the magnetic field through the center of these loops. Now I'm going to just carefully try and draw this so we get an idea that the magnetic field passes in between these loops. And the idea is that by concentrating and creating a length of loops, we are focusing more of the magnetic field inside the loops, but we know that the magnetic field has to cycle back somewhere on the outside too before going back through. The magnetic field is circular. So by trying to collimate it and straightening it out, we're also making a region in space out here where the magnetic field is getting closer and closer to zero. By straightening out this part, the magnetic field tends to spread out away from the solenoid sides and gets focused and collimated inside the solenoid. We're going to see how this works in just a minute, but a simple solenoid is one of the best and easiest ways to make a collimated magnetic field. Now, solenoids in general are used for all sorts of things. All sorts of things. I just want you to know that a solenoid is the #1 most effective way to make a single-use actuated device, which sounds really complicated, but I want you to think door lock of your car. It's not a motor. The door lock of your car has to push something one way for a short period of time, and then later on has to, make it move the other direction for a short period of time. Most of you don't have mechanical push buttons anymore. Most of you have something that will automatically unlock or lock all the car doors. And a solenoid is used for that, usually by interacting with a permanent magnet. So you turn on the solenoid, it pushes out the permanent magnet. You flip the current and it pulls in the permanent magnet. And probably at some point in your life you sat playing with the door lock of your parents' car, locking it and unlocking, watch the whole thing pop up and down, and your parents finally told you to knock it off. But deep down inside, you still like to do that. For some weird reason, the idea that you have this ultimate power makes you feel great. But if you open up the car door, you're going to find a small solenoid. It's just going to be a wrap of wires, about the size of a roll of coins. And that's what's used to unlock and lock the car door. Now, solenoids themselves are pretty ubiquitous. They're in all sorts of devices because they're an easy, straightforward way of creating a magnetic field. You want to really impress me, because I've been unable to do it, and I'd love to see one of you guys do it, is I would like to replace the permanent magnets that we use in our electric motors with solenoids, using a single battery to both power the magnet and the coil. I haven't been able to make it work, but this year, you guys were very successful with the electric motors. So that's kind of what I'm thinking about doing on Thursday. It's going back to the electric motors and seeing if we can make a truly independent electric motor where the magnetic field and the coil all come from the same current. It's not as easy as it sounds. I've been trying to do it for years, and I am terribly ineffective at it. But you guys might be better than I. That's what I'd like to see. So let's talk about proving the solenoid. If I were you, I would spend sufficient time drawing what I'm about to draw. And I would encourage you to, if you have multiple colors, consider using multiple colors. The top row didn't come out as good as the bottom row. You're going to want a row of circles like this. I have, 10, 13 circles there. The idea is to pair them up. Each circle actually represents a single coil in a solenoid. So we are looking at a cutaway of a solenoid. In this drawing, I'm having the current come out of the top and in on the bottom. And so, I'm going to put a little dot in each one of these circles. And a little X in each one of these circles. And if you want to see this better, you should open up your textbook, because in the textbook, of course, somebody has carefully printed this out. But for me, this is how it has to be done. This, in effect, is creating a solenoid. Now, consider just one wire for a moment. If I were you, I'd pick a wire on the end, and using your right-hand rule, verify the direction of the magnetic field around that wire. Do one on the top and one on the bottom. This should help you verify that inside the solenoid, we're getting an amplification of the magnetic field, that the contribution from the top and the bottom are in the same direction inside the solenoid. But you should consider that, and if I were you, I wouldn't draw this. Oof. If I were to continue to try and draw this, the upper magnetic field, which I'll now put in green just for the time being, is in that direction. But the lower magnetic field is going to be in that direction. I want to point out that the upper and lower wires together cancel the magnetic field out outside the solenoid. That the magnetic fields are in opposing directions exterior to the solenoid. Now, yeah, I agree with you. The red magnetic field at the top there has to be less than the green magnetic field that's right next to it. But remember how in capacitors, we indicated that the electric field outside the capacitor was more or less zero because of the contribution of both plates of charge? That's the same kind of effect we're going to get here. That as long as we have a very long solenoid where it's wrapped in such a way that it's much longer than it is wide, then the contributions to the magnetic field outside the solenoid will cancel out. So that effectively outside the solenoid, we get a net magnetic field that's nearly zero outside the solenoid. And we assume a relatively uniform magnetic field inside the solenoid. These are the assumptions we're going to make for a solenoid. They're not great assumptions. That's why you have to hear words like a very long solenoid or a solenoid that is longer than it is wide. We know that what we're about to prove for the solenoid isn't probably perfect. What we're going to do is we're going to use Amperes Law. But unlike a loop, we're going to draw a very defined rectangle. And I'm going to label a rectangle with the corners A, B, C, and D. Look, I'm here in motion in the hall soon enough. Amperes Law in this case is kind of funky. We've done this before with Gauss's law, but with Amperes Law, it's going to be kind of funky. We're going to take a look at just this portion. And remember those conditions I just talked about? We're going to break up our integral into 4 integrals. An integral that goes from A to B, plus an integral that goes from B to C, plus an integral that goes from C to D, plus an integral that goes from D to A. Now, it should be obvious here that the one that goes from D to A, it's got to be 0. The magnetic field is 0. Less obvious is A to B and C to D are also 0. And that's because the magnetic field passes in this direction, but my loop goes in this direction, thus the dot product produces a 0. So A to B is going to be 0, and C to D is going to be 0. Meaning the only contribution to Amperes Law is the part of the loop that goes in the direction of the magnetic field, B to C. Which means that whatever length loop I choose here, usually a lowercase l is used for that length, we'll get B dot L as the solution of the integral of B dot ds. All right, well, that'll be just fine for me. Using Ampere's law in this way is similar to when we use Gauss's law. By choosing our shape carefully, we were able to create an integral where pieces of the integral were cleverly made to be zero, while other pieces of the integral contributed to our flux. And we're doing the same thing here, where we don't have flux, but we're choosing a shape where some of these portions are clearly zero, and some of these portions are contributing to calculating the magnetic field. Now, just a reminder, we are summing the magnetic field over a length. So our answer has a length in it and the size of the magnetic field. And our goal is always, in these cases, to make sure that we are carefully selecting a shape that we can successfully integrate, with the hope being that we don't have to integrate at all, that we can kind of mathematically cut out the integral as much as possible. Now, the likelihood of having to calculate the magnetic field inside a solenoid is probably low, but you never know. It's one of those things where solenoid questions show up a lot, but they show up a lot because solenoids are actually used a lot. That's what we're going to build on Thursday, are solenoids. So we've taken and we've drawn a rectangle in here, and this rectangle I've given the labels A, B, C, and D. Crinkle that any more, and I'm going to freak out. So who's crinkling back? All right, two. Wow, it's a banner day. So here we go. I want to remind you about why it is that parts of this are zero and why parts contribute. A to B and C to D are zero for the same reason, that when we calculate B dot ds, we are calculating a dot product. And a dot product means that the only part of the magnetic field that contributes to this calculation is the magnetic field that's in the direction of our shape, our loop. So since B is up in the direction that we are integrating and CD is down in the direction that we're integrating, we assume or believe the magnetic field in this region is to the right. So the integration in that region is got to be zero because the cosine of 90 is going to yield a zero. And we don't have to worry about this region because the magnetic field's zero, or we are expecting it to be nearly zero outside of the solenoid. Again, making the assumption that our solenoid is very long compared to its width. Now, these are in many cases, although reasonable assumptions, they are in some cases not true assumptions. We know the calculation we're going to get is an estimate of the magnetic field in the same way where we calculated the capacitance of a parallel plate capacitor was really more of an estimate because we ignored the effects of the edges of the capacitor. We are ignoring the effects of those similar traits of a solenoid. So when we go from D to A, we're in the exterior of the solenoid, so there's no magnetic field there. That contributes to a zero. But when we go from B to C, it's the only place where we believe we have a magnetic field. We also believe that along that line, the magnetic field is constant. So the only thing that we have left then is B dot the integral of ds as we go from B to C. And that portion of our integral is just the length of our Amperian loop, which for right now is just an arbitrary number. And this is actually somewhat important that you understand that this arbitrary number, L, represents the length of the Amperian loop. Now, that length has showed up before when we calculated the magnetic field around a current carrying wire. That's where we got the 2 pi r. That length also existed when we did a loop of charge. A loop of current. We had the r in there for the radius. So this shows up, this idea of a length, but we're probably not going to keep the length there for very long, and I'll tell you why. Our other side here has got to be mu naught times the I enclosed. Well, The I enclosed is a little bit trickier to talk about here because in my calculation, my drawing here, I've encircled 4 current carrying wires. But I don't want to assume that I picked a specific number of wires. I am going to assume that there were n number of wires that were encircled by my Amperian loop. I'd put that in your notes here, that I'm not picking a finite number. I'm choosing a capital N to represent the number of wires that are actually encircled in the loop. That's what that capital N stands for, the number of wires that are encircled in the loop. I'm going to go for a 4th time. That capital N represents the number of wires that are encircled in that loop. Not a finite number. I didn't draw a picture here knowing it was 4. Just like I didn't pick a length. This is important because when I bring all of this together, I'm going to have mu naught times capital N times the current that's in the solenoid. That's the amount of current enclosed. Since I encircled only the bottom wires, all of those currents are in the same direction. So they all contribute in the same way to my enclosed current. This is going to equal B times L. Now this produces a magnetic field, and I'm going to collect things the way I would like them to be collected. U naught I for sure, but then I get this ratio of N over L, which we're going to call the wire density. The units are per meter, which is an odd kind of unit here, but it really is the number of wraps per meter. The number of wraps per meter. Now, the magnetic field for a solenoid is pretty straightforward, pretty simple. And one of the things I do want you to notice here is that it is heavily dependent on the wire density. Making a magnetic field is all about ramping up the current, which is all about concentrating as many wires as possible. You guys saw how thin that wire was that we were using for the motors. The reason for it is quite simple. I want to be able to pack a lot of wires into a small space. So we strip off all of the plastic coating. We enamel the wire to make the actual coating on the wire as thin as possible. That way we can pack more and more wires together. The more wires we can pack together, the stronger we can make our magnetic field. Look, if you want to make a magnetic field of just 1 Tesla, imagine what these numbers have to be to make that happen. A 1 Tesla field is a pretty big field, but as you've seen, we've done plenty of calculations where they're talking about 1, 5, 6 Tesla fields. What does it take to make that a 1 Tesla field? Take a look at the numbers for just a minute. What would you have to do? Remember what mu naught starts out at 4 times 10 to the negative 7th. Well, 4 pi times 10 to the negative 7th. The permeability constant is right there in the middle, starting you off at times 10 to the negative 7th. So if you want to get a 1 Tesla field, I mean, you can't get more than an amp or 2 through the wires before the wires start to heat up dramatically. So we're really talking about ramping up that wire density, trying to pack hundreds of wires per square meter. Per square millimeter. I mean, just put it in perspective. If you can get 100 wires per square millimeter, that's still just 10 to the 5th in your wire density. You still have a magnetic field that's 10 to the negative 2 Tesla. That's why it's so hard. What's funny? We're not laughing today. No jokes. Unless they're at Andrew's expense, or Brandon's, or Adam's, Or Katrina's. Happy birthday. So, what? Well, it's hard to make a strong magnetic field. Now, how many of you have things? There are several things so far in this chapter I've really recommended that you know. And I'm going to continue that and clearly add to it. Sometimes I'll write this two different ways. I want you to be prepared for it. None of these are on the equation sheet, but you should commit these to memory. One of them, of course, is the magnetic field around a current-carrying wire. One of them is the magnetic field at the middle of a current loop. And one of them is the magnetic field due to a solenoid. Lowercase n is just wire density written as a single letter, as opposed to writing it as a physical number of loops per meter. Now, there are other types of electromagnets. The most common is a toroid. Haven't seen a toroid question in a really long time, but just to ensure that we're being as complete as possible before I move on to something new, I want to talk a little bit about what a toroid is. In general, a toroid starts as a donut. And often, not that. A toroid just takes the idea of a solenoid and does your wire wraps all the way around until they come around the other side. I'm not going to draw the little loops all the way around this, but I think you can imagine what I'm talking about. Interestingly enough, toroids produce a very powerful magnetic field. You can probably imagine why. Part of it's just the reinforcement of that field due to the circular nature. One of the things that I've left out of all of this is so far we've had nothing but a vacuum inside our magnetic field sources, our wires and our current loops, and then before us the solenoid. To have an open air tube like this to create a magnetic field is actually not particularly useful. Just like dielectrics, we tend to find materials that we can put inside the location of our magnetic field to help enhance the magnetic field. The problem with this is that, of course, then there's an object there. If you want to be where the magnetic field is and there's a big object in your way, you're kind of stuck. But that was the same for parallel plate capacitors as well, that if you wanted the electric field to maybe accelerate particles, you wouldn't put a dielectric between the plates. But if you're interested in using that magnetic field for a different purpose, you would put something inside the coils. So like a dielectric, we often have cores to our magnets. A core serves the same function as a dielectric. It puts a material inside where the magnetic field is going to go that perhaps will enhance the size of the magnetic field. And that shouldn't be a surprise that we'll use things like iron and other paramagnetic materials. I don't know if you guys have heard that word before. It's a middle school word. No, paramagnetic, but thank you. Iron might have been a hard one. I mean, I'm assuming the word ferromagnetic might be new to you, but that's not a big deal. That's just an iron magnet. But paramagnetic, have you guys heard this word before? It's not really a vocabulary word for us. It's used to describe materials that are magnetic when a magnet is present. So like a paper clip will stick to a magnet. That suggests that a paper clip is paramagnetic. There are plenty of metals that will not support a magnetic field. Stainless steel doesn't support a magnetic field. So you can't stick a magnet to the front of a stainless steel fridge. But most of the fridges that, aren't stainless steel are made of something that is paramagnetic. So a magnet will stick to it. So there are plenty of metals that, that do not have magnetic properties. And it's actually supposed to be a middle school topic, but we'll talk a little bit about permanent magnets for a minute. Paramagnetic materials aren't necessarily permanent magnets. They can hold a magnetic field for a short period of time, but will usually lose it over time due to natural motion of the molecules. Permanent magnets can hold a magnetic field for a very long time, and they're made naturally in the Earth due to the fact that the Earth has its own magnetic field. Iron being one of the most common and abundant permanent magnet materials. That's why we talk about ferromagnets. Lodestones, ferromagnets, the original compasses used for navigation are all made out of iron. Now, to get an idea about the way we deal with permanent magnets is to understand that a magnetic field still can only be made by the motion of charged particles. So at the heart of any permanent magnet must be a charged particle that produces a magnetic field. Generally, materials that can sustain a magnetic field have outer shell valence electrons in S-style orbitals. And since I allow for electrons to travel in a looped circle. Now, not all of them are. A lot of the S orbitals are somewhat spherical and don't support this, but several of them aren't. Several of them are more oblong shaped, especially as you get to larger atoms. Because of that, the orbital of that particular electron forms a single current loop. So the motion of the one electron, just as we have it now, would produce and by the way, what direction would the magnetic field be produced here? If we assume this thing is spinning with its spin direction up. So if I was to try and describe for you what direction that electron is spinning, it's spinning in an orbit like this, so that I would wrap my hands upwards. What would be the direction of the magnetic field produced by this electron? I'll wait, that way I can call on somebody. Come on, in that loop. So now this current loop is in the plane of the board. I would hope that most of you would detect that there is a magnetic field at its center that's out of the board. Now, what I'm describing right now is an electron that's not orbiting in the plane of the board. It's orbiting in the plane of like your desk. So it's orbiting horizontally. And I'm trying to figure out the direction of the magnetic field from this single orbiting electron. So it's going to be up or down. And I want to remind you that it's an electron. So whatever the right-hand rule tells you, it's the opposite. So that's what I would expect. Now, I'm not trying to confuse you. I am trying to ensure that we know an electron is a negative particle. Its orbit should create a magnetic field. And if it orbits in a circular path, that magnetic field will be through the center of its orbit. And it will be in the opposite direction that the right-hand rule would give. Now, you could have just wrapped your fingers in the direction that the particle's going, or you could have wrapped it as if it were a wire. Either one of them should have helped you figure out the direction of the magnetic field. Either way, and this is what's important to me, that means every atom in a piece of iron has the potential to have its own magnetic field. That doesn't make iron magnetic. But inside a chunk of iron, there tends to be bits of crystalline structure called domains, where groups of atoms are lined up due to their natural magnetic field. You can imagine one magnet attempting to align itself with another. That crystalline structure tends to get fragmented over time. So if you just grab a piece of iron, it won't necessarily have magnetic properties, although individual bits of it do. Because all of those magnets are not aligned in one direction, you tend to get something that is haphazard. Imagine a small piece where there are lots of magnetic fields, but they are all in random directions. The net result would be no magnetic field at all. But like I said, the Earth produces magnets. Any volcanic lava flow, any upsurging in the ocean, any source of magma, which is heavily laced with iron, is going to bring liquid iron into a region of the Earth where there is an ever-present magnetic field. As that iron cools in the magnetic field of the Earth, these domains attempt and begin to line up, producing what we would call a permanent magnet. It doesn't have to be necessarily strong. The magnetic field of the Earth is not particularly strong, but as a liquid goes, there will be a reinforcement for each domain that aligns itself with the one next to it, a process that will build, so that when it hardens, you now have a permanent magnet. This is how you create one in the lab. This is how you would make one if you were trying to fabricate magnets. All you need to do is melt the iron, apply a magnetic field to it, and then let it harden. Cheap magnets are made this way all the time, usually filled with plastic and other cheaper materials than the iron itself, and then put on your store shelves wrapped in plastic so they don't scratch your surfaces. Now, at the same time, these aren't particularly strong magnets. But this idea of this magnetic replenishment in the Earth actually has several useful purposes. One of the things is we know that the Earth's magnetic field changes. We have a geologic record of it. As we go back through geology and look at layers of sediment or look at some of these upwelling areas where new Earth is being created, we can see changes in the direction of the magnetic field, layers, where there's different layers where magnetic fields are traveling in different directions. This is how we know the Earth's magnetic field reverses itself every so many years. Last time I read about this, about every 50,000 years, the Earth's magnetic field goes into flux. We are in the process now of the Earth's magnetic field shifting. It's not particularly dramatic, but it's measurable. Magnetic north no longer lines up with actual north, and it's drifting more and more every year. We have no idea what causes it. Eventually, there's going to be some issues probably. Right now, we're just renumbering runways because they no longer line up with magnetic compasses. So we will. If the current is traveling outwards in these spokes, then using your right-hand rule, could you tell me what direction this wheel would turn? Would it be clockwise or counterclockwise? Take 60 seconds. I'll call out one of you. More than just imagination, it might really require you to take a good look at your diagram. Let's see if I can do this. Not so much. So, I want you to think that current is a motion of positive particles in the wire. This positive particle is moving upwards in the wire, but the entire bar is moving instantaneously to the left. Correct? Now, this part's hard. Let's see if you can do it, though. There is a velocity to the left. The positive particles in the wire are moving upwards, but also to the left, because they have current, but there's also motion in the wire. What is the magnetic force on the positive particles? This is different than the force from the current. You have to do velocity that way, magnetic field into the board, and your thumb is downwards. Now, pick any of these wires, and you will find that there is a force on the particles back towards the center. Now, as I said to you before, there are limiting factors in physics. Limits to what can happen. This can't spin forever out of control. As the wheel increases its velocity, which, by the way, that velocity comes from the interaction of the current and the magnetic field. That very same magnetic field acting on those very same particles begins to disrupt the current by applying a backwards EMF that reaches a steady state, meaning there's a back EMF in the wire, a voltage in the wire back towards the center. That counters the external EMF that was causing the current in the first place. So the same thing that makes the wheel turn creates the conditions for a force on the particles to slow their movement. That phrase, back EMF, is going to come up a couple times throughout the course of this year. The back EMF has significant consequences for our circuit design. So if you were asked to figure out what this motor would do, and I was asked about the velocity of the motor over time, it would attenuate. It would reach a steady state condition where the external EMF that causes the current will be balanced by the back EMF due to the motion of the spokes. So again, if we just assume for a moment there's no current at all, but we have this magnetic field everywhere here with no motion of the charged particles, the motor does nothing. It does nothing, it just sits there in the magnetic field. These charges are there. Now, if I were to grab the wheel and spin it, not apply a current, just grab the wheel and spin it, charges in the wire, positive charges in the wire will all experience forces because they're trapped in the wire. So if I create a velocity in that direction, use your right-hand rule, I will be creating a current in the wire this way. And I'll do that for every charge. I will be creating a current in this way due to the motion of the wheel. That's the motional EMF that I am creating. Those positive charges would settle in the center. I would get negative charges around the outside, and I would have created an EMF. Now, we did the reverse of that. The motor established an external EMF, something that was touching both the in and out of the motor here. I guess the current was this way. And this generated a current in the wire. It was pushing the positive particles outwards towards the end. That interaction with the magnetic field caused the system to begin to move, but that motion also then creates another force that limits the motion of the system. Let me put it another way. And maybe for those of you who are a little wondering, like, why would nature work this way? Power equals voltage times current. And power equals the rate at which energy is consumed. When the motor's operating, it will have a finite kinetic energy. It would have to. That finite kinetic energy would have to be related to the rate at which the power is consumed by the motor. I would assume this current will be limited by factors like resistance and now this back EMF, limiting how much kinetic energy can be delivered to the motor. All right. Start showing you graphs that look, pick the graph that represents the magnetic field inside the wire. Well, there's going to be one where it shows R here and the magnetic field there, where this represents the outer radius of the wire. They will have one that looks like this. And they're going to have another one right next to it that looks like that. And then they're going to want you to recognize that although that's true inside the wire, let me get this written down first so we don't forget. That the moment we get outside the wire, we go back to our standard magnetic field outside the wire. Right, this is the magnetic field we have for outside a wire. We know that when we get to the radius of the wire, when R equals big R, the magnetic field will be that, right at the edge of the wire. And then the moment we get outside the wire, R still, little r, still someplace outside the wire, we've done this before, we get our standard decay in the magnetic field, a 1 over R decay. Look, there's multiple choices where you got to pick out which one of these represents the magnetic field outside the wire. They'll go as so far as to put 1 over R in this region and also have one of these graphs that'll look exactly the same. And they'll put 1 over R squared here. And just ask you which one of these represents the magnetic field as you go from the inside of a wire to a point outside the wire. And you'll need to know this is the right answer. And they will not only be comparing it to this, but they'll be making sure you understand that it's not an R squared drop, that it's a 1 over R drop. This is on the multiple choice if you're having to think fast. So, getting back